Motivated by the two examples we have seen in the previous module, that summation 1 by n squared converges and summation 1 by n diverges, let us formulate and prove this theorem, which is the famous Cauchy condensation test. Cauchy condensation test. The test is as follows. Suppose Bn is a decreasing sequence of non-negative real numbers. Then summation n equals 1 to infinity Bn converges if and only if summation 2 power n b 2 power n equals 1 to infinity converges, right? So this can be written as b1, oh just a moment, this is actually n equals 0 to infinity. The reason is that 2 power 0 is 1. So this is b1 plus 2 b2 plus 4b4 plus dot dot dot. So the convergence of a series of non-negative terms that are decreasing is determined by the convergence of this new series, which actually has terms that are sparsely coming from Bn, but to account for the sparsity you are multiplying by a exponential. Okay, let's prove this. Proof. Suppose summation 2 power n b power n converges, n equals 0 to infinity. Okay, now what I do is, we already know that the sequence of partial sums of Bn are increasing, right? Simply because the sequence Bn is non-negative. Because of that, the sequence of partial terms will be increasing. So what I'm going to do now is I'm going to determine what Sm is using the fact that this series converges, summation 2 power n b power n. How do I do that? Well, fix m greater than 2 power, not greater than, less than or equal to 2 power k plus 1 minus 1. Okay, fix m like this. Then the sequence of partial sums Sm is certainly going to be less than or equal to S 2 power k plus 1 minus 1. The minus 1 is still there in the subscript. Okay, this is simply because, as I just remarked, the sequence of terms Bn is non-negative. Therefore, this series of sequence of partial terms will be increasing. Fine. So how does this help? Well, we pull the same trick, which is very similar to what we have already seen in showing that summation 1 by n squared is convergent. This is nothing but b1 plus b2 plus b3, which we group together, plus b4 plus b5 plus b6 plus b7, which we group together, so on. And finally you start at b2 power k, go all the way up till b2 power k plus 1 minus 1. Okay, now because this sequence is a decreasing sequence, Bn is a decreasing sequence, we have this is less than or equal to b1 plus 2b2 plus 4b4 plus dot 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 2 power k b 2 power k. Right? Simply because this is a decreasing sequence. So, what have we got? We have got that this is nothing but tk, where tk is the sequence of partial sums of summation 2 power n b 2 power n equals 0 to infinity. Right? So what we have actually established is that the sequence Sm is actually bounded above. Because we have established that if you take the mth term where m is less than or equal to 2 per k plus 1 minus 1, we have got that Sm is in fact less than or equal to tk. Therefore, the sequence of Sm is actually bounded above because this sequence tk is bounded above. Why is the sequence tk bounded above? Simply because the sequence tk converges. That's the hypothesis. Therefore, Sm is actually bounded above. By monotone convergence theorem, we are done. Okay. So now if you carefully look at the statement, it says if and only if. What we have shown is we have assumed that this converges. We have now shown that summation n equal to 1 to infinity bn converges. The other side is very, very similar to showing that summation 1 by n is divergent. So I'm going to leave it to you. Show that if summation 2 power n b 2 power n equals 0 to infinity diverges, then so does summation n equals 1 to infinity bn. Okay, this is exactly similar to the proof that summation 1 by n diverges. Now immediately we have an application of this Cauchy condensation test. Example, we already know that summation 1 by n diverges. We already know that summation 1 by n squared converges. Now what happens in between? Well, if p greater than 1, then summation 1 by n power p converges. So p equal to 1 is sort of like the boundary. When p is greater than 1, it definitely converges. When p is less than or equal to 1, it diverges. You will deal with the case less than 1 in the exercises. Okay. Suppose you have summation n equal to 1 to infinity 1 by n power p converges. I am going to apply the Cauchy condensation test. Why? Because it is coming in that lecture. Well, that's not the reason. You will see in a moment why the Cauchy condensation test is very applicable. What we have to do is we have to consider this new sequence summation 2 power n 1 by 2 power n power p, n equals 0 to infinity. Okay. Now why is this helpful? Well, what you can do is you can just pull this little trick. This is nothing but n equals 0 to infinity 2 power n by 2 power p power n, which is nothing but summation n equals 0 to infinity 2 by 2 power p power n. Okay. Now, one thing you should be careful about, this is a rather pedantic remark. The manipulations I have done here about equalities, note this is not really in a number unless it converges, right? A series, you can treat it as a number only if it converges. Otherwise, it's just a formal expression. Please recall that our definition that a series is a formal expression. What I mean by equal to here is that of logical identity. All I have done is manipulated what Bn is. So I am just asserting that this series formally is same as this series is formally same as this series. I am not asserting anything about convergence and such things. Okay. Now it will turn out that because these three series are logically identical, I have just manipulated the form of the expression Bn. If one of these series converges, then all of these converges and the number are going to be the same. The number to which it is converging is all going to be the same. This is a slightly pedantic remark. Okay. Now, coming back, we have 2 by 2 power p power n. Why is this helpful? Well, 2 power p is strictly greater than 2 because p is greater than 1. Because p is greater than 1. So, because of that, this just becomes a geometric series. A geometric series. Okay. It becomes a geometric series with first term 1 because n is 0. First term 1 and common ratio r equals 2 by 2 power p. Okay. Now we have already seen that if r is less than 1, this series converges. Okay. Hence we are done. So we have established that this series summation 1 by n power p converges if p is greater than 1. Okay, this is an application of the Cauchy condensation test. Now coming to the second topic of this module, that's Cauchy's convergence criterion. This is a very easy thing simply because we have already applied this several times when studying sequences. So suppose Bn is a sequence. So let me just use consistent notation. I have chosen to avoid putting the parenthesis whenever possible. So suppose Bn is a sequence, and yeah, let me just leave it at that. Suppose Bn is a sequence, then the series summation Bn n equals 1 to infinity converges if and only if for each epsilon greater than 0 we can find capital N epsilon such that if n comma m greater than capital N epsilon and n greater than m, we have modulus of sum n, or I should not use n, I will use j simply because there will be repetition, j running from m to n of Bn. This modulus is less than epsilon. Okay. So this might seem a bit complicated, but once you see the proof, you will just facepalm yourself and think, oh, it's obvious. Proof. Well, the sequence of partial sums, just one moment. Let me just, for increased applicability of this result, put n greater than or equal to m. Okay. Really, the sum still makes sense. The sequence of partial sums, say sk converge, and therefore sequence, okay, I shouldn't write this, converge if summation Bn converges, right? And vice versa. So the sequence of partial sums converge if summation Bn converges and vice versa. That's just the usual Cauchy criterion for convergence of sequences. Okay. Sorry. That's just the definition. Sorry about that. Therefore, summation Bn converges if and only if Sk is Cauchy. This is where Cauchy convergence criterion comes into the picture, not the previous sentence. Sorry about that goof up. So, summation Bn converges if and only if Sk is Cauchy. But Sk is Cauchy gives me n epsilon such that if n comma m greater than n epsilon and n greater than or equal to m, then mod Sn minus Sm is less than epsilon, right? That's what Cauchy's convergence criteria is. But this is just the sum that we are interested in. Summation Bj j running from m to n. This is exactly that sum. Okay. So this is just I don't know what to say. This is just a proof by translating what the hypothesis is saying. So there's nothing really happening. You have just reduced it to the Cauchy convergence criterion for sequences. So both directions follow immediately because you can just reverse the steps in the proof we have written. Okay, hence proved. We get an immediate corollary, which is a very, very useful criterion for determining that a series diverges. Corollary: a series that is convergent, a series summation Bn that is convergent must have Bn going to 0. Okay, I'm not even going to insult your intelligence by writing a proof. This just immediately follows from Cauchy's convergence criterion. So the nth term of a convergent series must converge to 0. Okay, so the converse of this corollary is not true. So let me write that in bold because people make that mistake. Okay, converse. Okay, this is a very ugly color. Not true. I'm going to permanently imprint this in your head. Converse is not true. Do not make that mistake. If the nth term goes to 0 does not mean that the series converges. Just take summation 1 by n. That will give you the example. Okay. So that's it for today's module. This is a course on real analysis and you have just watched a module on the Cauchy condensation test and Cauchy's convergence criterion.